All right. So can somebody tell me what an electric field is or an electric force? You must have seen this in chapter 20. Is it 20? Somebody? Electric fields, what causes, at least let's go slowly. What causes an electric force? Or electrostatic force? What causes an electrostatic force? What's the source? What's responsible for an electrostatic force? Is it a mass? Is it the planet Earth? A charge? Electrons? Yes, that's true. Electrons create forces around them. It's called an electric force or electrostatic force if the force is not changing with time. Okay, so all charges create electrostatic force. It can be electrons, it can be protons, it can be positive charges, negative charges, it can be ions. Okay, take an atom, a neutral atom, and remove an electron from it. It becomes an ion. The ion itself creates an electric force. Okay, and all around it. Okay, all around it, it creates an electric force. Okay, and the collection of all those electric forces in the space around the charge, that's what's called the electric field. Okay. All right. So now, what does an electric force do? Somebody, what does an electric force do? It has an effect on other charges. It pushes away other charges or pulls other charges. Okay. Let's say I have a negative charge, which is the source, repairs and attracts, yes, which is the source of the electric force. If that, if there is so I have a negative charge, which is the source. If there is a positive charge in the vicinity of that electric charge, of that negative charge, what will happen to the positive charge? They will attract. It will be attracted by the negative charge, yes. And if there's another negative charge, what will happen to it? It will repel it. Okay, it will repel it. Good. So all right, so you understand this. Okay, so now in a circuit, okay, like the ones that we dealt with in the last lab, what causes the electrons to move? Because you saw that there was a current, right? The current, by definition, is the motion of charge, motion of electrons. Okay, it can be electrons, it can be positive charges, it doesn't have to be electrons, but typically in our electric circuits, most of them, it's electrons that are moving. Okay, so what causes those electrons to move? Does anybody know? There is an electric force, or there's an electric field in the circuit, in the wires, and that electric field is what pushes the electrons. Okay, and that's why they move, and that's where the current comes from. Okay, all right, so you know everything about electric forces and electric fields. What about magnetic forces? What creates a magnetic force and a magnetic field? A magnet. Yeah. a magnet, yeah, that's one way, okay? So an ordinary naturally occurring magnet can create a magnetic field around it, okay? And what does the magnetic field do? It has an effect on charges also, just like the electric force, okay? And it pushes charges away, it makes charges move, okay? That's what magnetic forces do. That's why they're important, okay? They move around charges, just that magnetic forces have an effect on charges that are already moving, okay? While electric forces have an effect on charges that are moving or stationary, okay? An example of, okay, now, apart from magnets, do you know of anything else that can create a magnetic field around it? Anybody of anything else? No? A current, okay? A current, an electric current, creates a magnetic field around it. Have you seen that in chapter 22? Have you seen that an electric current creates a magnetic force? Radiation waves. Well, radiation waves, yes, that's true. Radiation waves, they are a collection of electric and magnetic fields. They are a collection of electric and magnetic fields that are propagating through space or through a medium. But a current can create a magnetic force. Okay, so you probably haven't seen that yet. Okay, so that's one important fact that you have to remember. Okay, a current creates a magnetic force and therefore a magnetic field all around it. Okay, if you have a wire and there's a current running through the wire, it's going to create a magnetic force around it, a magnetic field that will push away charges. Okay. Now, okay. Yes. Now, an example, a good example of a magnetic, of a source of a magnetic field is Earth, planet Earth. Planet Earth itself is a huge magnet. It's a huge magnet. And it creates a magnetic field all around it. Okay? And we all live in Earth's magnetic field. We all live in Earth's magnetic field. Okay? And you can see its effect with a compass. Okay? A compass in Earth's magnetic field, it gets deflected by Earth's magnetic field and points to, and its needle points to the north. All right. But Earth's magnetic field is very important for life on Earth. Without it, without Earth's magnetic field, well, life wouldn't be possible because there are charged particles that come from the sun we are constantly bombarded by charged particles from the sun. Okay, and those charged particles, they may be they are protons, electrons. They would destroy our atmosphere. They would destroy our atmosphere. Okay, and without an atmosphere, we wouldn't have any air to breathe, and life would stop on Earth. What protects us from that is our magnetic field, because as we said earlier, the role of the magnetic field is to deflect charges, to push them away. Okay, so when the charged particles coming from the sun, uh, uh, when the sun, it's called the solar wind. The solar wind. When the solar wind comes towards us, Earth's magnetic field deflects those charged particles, and that's how we are protected. And that's what creates the auroras at the North and the South Pole. The charged particles, they get collected at the South and the North Poles, and they create the auroras. Have you seen the auroras on television? The northern lights. Okay, they are created by that phenomenon. Okay, somebody asked, what about the moon? Does it have a magnetic field? Well, to understand, we need to know why Earth creates a magnetic field. It creates a magnetic field because in its core, okay, so Earth is subdivided into layers. Okay, we live on the top layer, which is called the crust. There is a middle layer, which is very thick, which is called the mantle. And at the center, there is a smaller layer, which is called the core, okay, which is spherical. It's called the core, and it's liquid because its temperature is very high. Okay, it's liquid, and it's made of metal. Okay, but it's metal which is liquid, which moves around. Okay, it moves around, and because of temperatures are so high, there are many charges that move around. Okay, because of convection currents. Okay, convection. And because they move around, those charges, they create currents. That's what a current is by definition. It's the motion of charges. And because those currents, there are currents, those currents create magnetic fields. Okay? As a matter of fact, all magnetic fields are created by currents. Even in your magnet on your fridge, you may not realize it, but inside your magnet, there are small currents. There are small currents because there are electrons that are moving, and those small currents are aligned in such a way that they create a powerful magnetic field. And that's why your magnet, creates a magnetic field. It's the same process for Earth. The same process. Okay, there are currents that create a magnetic field, and that's possible for planet Earth because Earth's core is hot, and it's hot because Earth is big. Okay, it's very massive. It's very massive. It has a large mass. Okay, it's big, so it's hot. Okay, it's hot. So somebody asked about what about the moon? Well, the moon is small compared to Earth. And planet Mars is small compared to Earth because planet Mars and the moon are so small, they have cooled down over time. Okay, the solar system was created 4.5 billion years ago. Okay, and all these terrestrial planets, Mercury, Venus, Earth, Mars, even the moon, okay, and the other moons, okay. Mars has 2 small moons. They were hot, okay, and they had magnetic fields. They created magnetic fields because they had a core that was hot, but over time they cooled down, okay. They cooled down, and because they cooled down, they lost their heat, and the core hardened. Okay, and then couldn't produce currents, and therefore they lost their magnetic fields. But Earth still has its magnetic field. Mars doesn't have a magnetic field. Because Mars doesn't have a magnetic field, so you see, Mars used to have in an atmosphere, a thick atmosphere, and it used to have water on it, oceans and rivers. Maybe life, we don't know. We don't know, but it definitely had oceans, it definitely has had rivers, it definitely had an atmosphere, but it has lost all of that. It has lost its atmosphere, it has lost its rivers and its oceans. Okay. Why? Well, it still has an atmosphere, but it's very thin. It's very thin, nothing compared to what it was billions of years ago. So why did it lose its magnetic field? Well, it's because it cooled down, so its core is no longer hot. Therefore, there are no currents being produced inside, and therefore it doesn't have a magnetic field to protect itself against the solar wind. So the charged particles from the sun came and they took away the atmosphere. Okay, they broke up the atoms constituting the atmosphere. Okay, and it eventually lost them. Okay, and eventually it also lost its water. Okay, yes. So so all magnetic fields are produced by currents. Okay. And magnetic fields are very important. Okay, extremely important. That's how your remote control works. That's how your credit cards work. Okay, it's thanks to magnetism. That's the reason why we are able to see light. Okay, visible light, because electromagnetic radiation or light is a collection of electric and magnetic fields. So magnetism is a super important. Okay. Now, a very interesting phenomenon happens when the current is not steady, when the current changes with time. You understand? A current that doesn't change with time creates a magnetic field. But a current which changes with time creates a magnetic field which changes with time. You understand? And when that happens, that magnetic field itself creates an electric field. It creates an electric field. Okay. That's called electromagnetic induction. And this was discovered by Michael Faraday. Has anybody heard of Michael Faraday? Somebody who has never heard of Michael Faraday?
I have not.
You have not. One person. Only one person? Who else?
I have not.
Who has heard of Michael Faraday? Me. So Yana has heard of Michael Faraday. Who else? Shannon has. Nabila has not. Okay. Oh, no, Nabila has. No,
Wait, this is a weird stretch, but is he a basketball player?
Michael Faraday? No.
Oh, okay. Sorry.
He's not. He was a scientist, a British scientist of the 19th century. British scientist of the 18th, 19th century, mostly 19th century. He is very important because he made many very important discoveries. In the area of electromagnetism. Okay, he discovered Faraday's law, of course, which is named after him, of electromagnetic induction. Okay, the fact he was an experimentalist the fact that, as I just described, a changing magnetic field creates an electric field. Okay, and he also discovered many of what's called the Maxwell's equations. He also discovered in 1832 the motor, the dynamo, and the generator. Okay, I believe 1832. Does anybody know what a motor is? It's an electric device. Yes, Lillian knows what a motor is. Okay, all right. It's an electric device. Okay. Now, after discovering that an changing magnetic field creates an electric field, and the question is, what about a changing electric field? Okay, does it create a magnetic field? Okay. Well, an electric field, but we're not going to go into that. Okay, so so let me show you the equation. I promised you that I would show you the equation that will. So let me share my screen with you. No, this is not what I wanted. Is this what I wanted? Sorry, this is not what I wanted. Oh, okay, found it. Okay, can you see the title Maxwell Faraday equation?
Yes.
Yes, okay. So you see the top equation there, or you see the bottom equation, right? The bottom equation which has integrals in it. Do you see that? E is the electric field. B is the magnetic field. Okay, so you see that a changing dB dt is the change in the magnetic field. The change in the magnetic field creates, this equation says that the change in magnetic field creates an electric field. On the left, you have the electric field. Okay, so basically that's what the law is. That's Faraday's law. Okay, but in integral form. Okay, so you have it here again. The change in magnetic field creates an electric, and the magnetic field creates an electric field. Okay. But to be more exact, it's the changing in what's called the magnetic flux. But I'm not gonna go into that because that will be a little bit too much. You are going to see this next time you meet in lecture. Okay, what flux is. Okay, what flux is basically a combination of the area that the magnetic field is crossing and the magnetic field itself. Okay, you will see that in lecture. Okay. Okay, so you will see all that. So let's go back. Let me stop sharing. So a changing magnetic field creates an electric field. And if there happens to be a wire nearby, okay, since you are changing the magnetic field, an electric force and an electric field will be created in the wire, and that will move the electrons in the wire, and therefore that will produce a current. Okay, that will produce a current. So that's electromagnetic induction. Electromagnetic induction is super important in modern technology. Almost all of the modern technology that we enjoy, okay, relies very heavily on electromagnetic induction. I can give you many examples. Like, for example, your television. How are you able to watch television? Okay, this is possible because because let's say somebody, okay, for you to be able to watch television, watch the news, for example, the journalist has to talk through a microphone, but sound is a wave, it's a sound wave. The sound wave has to be converted into an electric signal, okay? For that to happen, you need a device which is called a motor, okay? And then that electric signal needs to be converted into a radiation, electromagnetic radiation, radio waves, which will propagate through space. For that to happen, you again need a motor. And then those radio waves needs to be converted again into sound in your television set or into pictures, okay? And that happens thanks to a motor again, okay? And it's Michael Faraday who discovered the motor in 1832. So radios and televisions use motors. Your cell phone, same thing. Your computer, same thing, uses motors, okay? Your DVD player, your compact disc player, okay? To record data on it, you need a motor, right? You need a motor, right? To turn signals, whether they are video or audio signals, into ones and zeros, okay? Digital signals, you need a motor. What else? How you get electricity in your homes, okay? How is electricity produced, okay? It may be hydroelectric power, right? You all know how electricity is produced. Can anybody describe? Does anybody know how electricity is produced? Hydroelectric, for example? No idea? And we are going to talk about it in this lab, okay? Electricity, hydroelectric electricity comes from, waterfalls, okay? That's one way, okay? You create a dam, and the waterfall, what the water does, it turns a turbine, okay? A turbine is basically a magnet, okay? When the magnet turns, the magnetic field that it creates changes, okay? And because the magnetic field changes, that creates, according to Faraday's law of electromagnetic induction, that creates an electric field. And the electric field in the wires that are nearby is what pushes the electrons, okay? Pushes the electrons, and that's what creates a current, okay? And the current is to be distributed across long distances. That current is typically a high voltage current, but then to be used in your homes, that high voltage current needs to be turned into a low voltage current, okay? And how does that happen? You need a transformer, okay? And how does a transformer turn a high voltage current into a low voltage current? You need a motor for that. You need a motor again, okay? And almost all forms of power generation are due to electromagnetic induction, okay? It's the same principle, a magnet that turns and therefore a magnetic field that changes, and that's what creates an electric field, and that's how electric currents are produced. Whether it's nuclear power, it's the same thing, okay? What the uranium does, it warms up the water, okay? It warms up the water, and the water becomes steam. And instead of the waterfall turning the magnet, or the turbine, because the magnet is attached to a turbine, it's the steam that turns the turbine, okay? Wind energy is the same thing. It's not the wind itself that turns the turbine, okay? And again, because of electromagnetic induction, the turbine turning creates a changing magnetic field, and therefore the changing magnetic field, thanks to Faraday's electromagnetic induction, creates a current, an electric field, and therefore a current. Coal, same thing, okay? Thermal power, same thing. Waves, geothermal, same thing, okay? All of telecommunication, whether it's analog or digital, uses motors, and therefore electromagnetic induction, okay? Magnetic tapes, electric trains, okay? When you travel, you go to school, you commute to work, you take electric trains. How do they work? Well, they are magnets, artificial magnets, which we call electromagnets, okay? That operate them, okay? That operate them. So all of modern technology relies very heavily on Microfaraday's discoveries: electromagnetic induction, the motor, the generator, and the dynamo, okay, which he discovered in 1832. And the funny thing is, Michael Faraday did not have any education at all. Well, he had just elementary school, so he could just barely read and write, okay? But he loved science, and he devoted his entire life. Yes, that's crazy. He devoted his entire life to scientific research. He was an experimentalist. He made, in class, you probably have seen, I'm pretty sure you have seen the feed lines, how we draw feed lines, electric field lines, magnetic field lines, and all of that. It's all due to Michael Faraday. Okay, he's the first one to have come up with the idea of drawing them like that. He made all those discoveries of, you know, all the most important laws in electricity and magnetism. And he only had elementary school education, but he loved science, so he spent a lot of time in his lab making all those discoveries, okay? And many people have said, and it's not, I think it's not an exaggeration, if Michael Faraday had not lived, okay, we wouldn't have the modern technology that we enjoy, and therefore we would probably all be farmers, and that's a possibility. And our cities wouldn't have any lights, okay, and we wouldn't have any electric devices, and all of electronics wouldn't exist. Okay, so that's how important he is. So now, any questions before we start the lab? No questions? Okay, so let's get started. Long introduction, but necessary introduction. So let me share my screen with you again. I have to find, where is it? All right. So can you see my screen? Can you see the magnet and the compass? Can somebody please can you interact? Excuse me?
We see your screen.
You see the magnet and the compass?
Yes.
Okay, thank you very much. All right. So here I have a magnet and I have a compass. All right. And you see, these are magnetic fields. All right. I have magnetic fields here. So if I move the magnet, yeah, it's a little bit hard to move, but you see that the compass gets deflected, as it should. All right. If I move the magnet, the compass gets deflected. Okay. It's because of the magnetic field lines. These are magnetic fields, basically. Okay. And I can show the field meter. Okay, so this is the meter. It measures the magnetic field. It's a vector. The magnetic field is a vector. So it has components, an X component and a Y component. It also has a Z component, but here to simplify, we are going to work in 2 dimensions. Okay, and it has a magnitude. The magnitude is the top number. Okay, 1.09. Okay, and these are the magnetic the components of the vector. All right. The bottom number is the direction of the vector. The vector has a direction, right? So it's 62.69 degrees. Okay, and that's just move the meter. You see that the numbers change because the magnetic field changes. Okay. Okay, so I think this is what's important here in this first part. All right. So now the next tab is pick up coil. Okay. So you see, I have a magnet, and then I have a coil of wire, and then I have a light bulb. All right. But then you see, you have the magnet, which is creating a magnetic field everywhere. Okay, magnetic field here, magnetic field here, and so on and so forth. So if I was to take an electron, okay, a moving electron, that's very important, if I was to take a moving, if I put an electron here, nothing's going to happen to it. But if the electron is moving, it's going to be deflected, or a proton or an ion, or any charge, okay? Because anywhere in space, because there's a magnetic field everywhere created by this magnet. But now, see what happens when I move the magnet. It's a bit hard to move. You have to be patient. You see, as I move the magnet, you see the magnetic field changes, doesn't it? And what do we observe when that happens? Somebody.
You can see that there are different, like depending on where you move the magnet, the forces can attract or repel. Like for north, it's attracted to the white part, and then for south, it's attracted to the red part.
Right. These red and white things, they are the magnetic fields themselves. So those magnetic, as I move the magnet, you see that they changed. Okay. These little things, red and white things, changed. Okay, the magnetic field, they changed. The magnetic field changed at every point in space when I move the magnet. But what about the coil of wire? The little blue dot are the electrons. Okay, and then the thing on top of it is a light bulb. What happens to the coil of wire, to the electrons and to the light bulb? Okay, let me move again. Okay, it's a bit hard to move. You have to be a bit patient. You can move it. Okay, I'm moving the magnet. It's a bit hard to move. Wish I could move it more smoothly. So what happened to the electrons in the wire? And what happened to the light bulb as I moved the magnet?
The electrons move and the light bulb lights up.
That's true. That's true. And when the magnet is stationary, nothing happens, right? Nothing is moving and nothing is lighting up. Okay. Now, based on my long introduction, can you explain why? What the difference is? If you remember what I talked about. Anybody explain? Try, I mean, we'll help, I'll help. Can you explain why when I move the magnet, the electrons move in the wire and therefore there's a current in the wire and therefore the light bulb lights up? Well, it's because of Michael Faraday's law of electromagnetic induction. As I move the magnet, the magnetic field changes. The magnetic field is these little things. How are we going to call them? These little things, they are vectors. They call them vectors because they are vectors. Okay, they are pointing in different directions. Okay, and yes, they're the magnetic fields. Okay, they point in the direction that the compass needle would point to. So as I move the magnet, you see that they change, their orientations change, but also their magnitudes change. As you can tell, if you bring the field meter, see, let me bring the field meter and put a field meter at a particular point, specific point here, and then let me move the magnet. You see, as I move the magnet, the components change, the magnitude change. Okay, the direction changes. everything changes, okay? And that's when the electrons move, and that's when the light bulb lights up, okay? It's because changing magnetic field creates an electric field, and the electric field in the wire is what drives the electrons, and therefore, because the electrons are moving, we have a current, and that current is what provides the energy to the light bulb to light up, okay? So that's the explanation. Now, so this is a magnet like the one on your fridge, okay? But in industry, we like to use electromagnets, okay? Those are artificial magnets, okay? How do we create them? Well, because we create them by running a current through them, okay? Because we've agreed that a current creates a magnetic field like Earth, right? At Earth's core, there's a current, okay? And that current is what creates Earth's magnetic field, okay? In the same way, if you run a current through a wire or several loops of wire, like in this case, you create a magnetic field, okay? Which is exactly the same as that of a magnet, an ordinary magnet. So that's why we call this artificial magnet an electromagnet. We call it an electromagnet, okay? Because it's a magnet that, you know, made by men, okay, or women, okay? It's an artificial magnet, and that's these are the kinds of magnets that we like to use in industry, okay? Trains are full of these, okay? And as I move it, you see that it creates a magnet. The magnetic field changes everywhere, as you can tell by looking at the compass. The compass needle, which is here, gets deflected, okay, because the magnetic field is changing, okay? All right, how about the transformer now? Okay. Now, if I take the electromagnet, okay, it's just like an ordinary magnet, and I move it, the magnetic field changes. But now look at the coil of wire and the light bulb and the electrons, and the coil of wire on the right, and tell me what happens to them. As I move, yeah, it's very hard to move these things. So what happened to them as I moved my electromagnet? What happened to the electrons in the coil on the right, and what happened to the light bulb? Oh, sorry, I forgot to remove you. Okay, I removed you now. So what happens to them?
We see that as we move the electromagnet, it did the same thing as the bar magnet,
Right.
and the light bulb light up.
That's correct. That's correct. Okay, so same phenomenon took place. As we move the electromagnet, the current is created in the secondary coil of wire, and therefore the light bulb lights up. That's electromagnetic induction. Okay. All right. Nice. Nice. I think you understand this. Now the generator. Okay. So this is a generator, a typical generator, right? So think this is Hoover Dam. Okay. Hoover Dam. It has a waterfall. Okay. The waterfall. There's water running, and then of course in the there's a turbine, okay, with a magnet attached to it. It's our turbine. It's a magnet and a wheel, Okay, and as it turns, as the turbine turns, okay, being pushed by the water, the magnetic field all around it changes. I'm not showing it, but if I want, I can even show it. Does it show the field? Yeah, it shows the field, and you see that the field changes. Let me increase the number of revolutions. Okay, the turbine is turning faster, and you see that the magnetic fields all around these little vectors, red and white, are changing as the turbine turns. Okay, and then in your homes, or okay, in the coil of wire next to it, you see that the electrons are moving, therefore a current is created because there's an electric field that's being created there, and then the light lights up. Okay, so that's how it all works. Are there any questions so far? No questions? I taught this lab last year, spring 2020, to physics 208 students. So you can find the video for that on my YouTube page. It's exactly the same lab, and I maybe go in more details into this simulation, or maybe less. I don't know, but that may help also. Okay. I think I called it electromagnetic induction. That's what I may have called the video. So if there are no questions, I'm going to stop the video. And then you can start working on your lab, and I will help.